What if our universe is not the only one? What if everything we know, space, time, the laws of physics, is just one version of many? These questions are no longer confined to philosophy or science fiction. In modern physics, they represent serious possibilities that emerge naturally from our most advanced theories. The idea of a multiverse, a collection of universes beyond our own, sounds extraordinary, but it is not a wild guess. It is a consequence. When scientists followed the logic of inflationary cosmology, quantum mechanics, and string theory, they did not set out to discover a multiverse. Yet again and again, the equations pointed in that direction. Tonight, we will explore one of the most provocative questions: is the multiverse real? For most of human history, the word universe meant everything, absolutely everything that existed, seen or unseen. It was a singular concept, both philosophically and scientifically. From ancient thinkers to early modern scientists, the idea that there could be more than one universe did not even enter serious consideration. There was just the universe, unique, all-encompassing, complete. In ancient Greece, philosophers like Aristotle imagined a cosmos that was eternal and unchanging. Earth stood at the center, surrounded by nested spheres carrying the moon, the sun, the planets, and finally, the stars. Beyond that, nothing. The stars marked the boundary between existence and non-existence. This geocentric model wasn't just a matter of astronomical convenience, it reflected a world view. The universe was finite, ordered, and complete. There was no room for other universes. Centuries later, the scientific revolution challenged that static vision. In the early 17th century, Galileo Galilei pointed a telescope at the night sky and saw something that shocked the world. Mountains on the moon, moons orbiting Jupiter, and stars too numerous to count. The heavens, once thought perfect and fixed, were dynamic and material. Around the same time, Johannes Kepler and Isaac Newton developed laws of planetary motion and gravity, transforming celestial mechanics from mystery into mathematics. Newton's universe, developed in the late 17th century, was infinite in space but eternal in time. It extended forever in all directions, filled with stars and governed by precise physical laws. Gravity reached across empty space. Time ticked forward steadily, unaffected by the events within it. This framework became the dominant model of the cosmos for the next 2 centuries. Even as telescopes improved and astronomical catalogues grew, the assumption held the universe was singular. Scientists studied the universe, not a universe among many. There were unknowns, certainly, but these were understood to be pieces of a single, coherent system. In the early 20th century, that idea was dramatically reshaped. In the year 1915, Albert Einstein introduced the general theory of relativity. It replaced Newton's concept of gravity as a force with a geometric view. Matter curves space-time, and that curvature tells matter how to move. General relativity provided a new way to think about the cosmos, not just as a stage where events happen, but as a dynamic entity that could evolve. Interestingly, Einstein himself was uncomfortable with the implications of his own equations. They suggested that the universe could not be static. Gravity would pull everything together, leading to either expansion or collapse. To counter this, Einstein introduced a term called the cosmological constant, a mathematical fix to keep the universe balanced and unchanging. He later referred to this addition as the biggest blunder of his life. Still, Einstein's equations opened the door for new models of the universe. Around the same time, a Belgian priest and physicist named Georges Lemaitre was studying Einstein's theory. In the 1920s, Lemaitre proposed a radical idea: the universe is expanding. He reasoned that if space is stretching now, it must have been smaller in the past. Tracing that logic backward led to a starting point, a primeval atom, as he called it, a moment when the universe emerged from a highly compact state. This idea was not widely accepted at first. Many scientists, including Einstein, were skeptical. But in 1929, American astronomer Edwin Hubble made a discovery that changed everything. Using observations from the Mount Wilson Observatory in California, Hubble measured the light from distant galaxies. He noticed that their light was redshifted, stretched to longer wavelengths. This redshift indicated that the galaxies were moving away from us. More importantly, the farther away a galaxy was, the faster it appeared to be receding. Hubble's data provided strong evidence that the universe universe was expanding, just as Lemaitre had predicted. The consequences were profound. If the universe is getting larger, it must have been smaller in the past. This became the foundation of what we now call the Big Bang Theory. The idea of an expanding universe transformed cosmology. No longer was the universe seen as eternal and unchanging. It had a history, it had a beginning, and that meant it could have a structure more complex than previously imagined. Despite this shift, the expanding universe was still the universe, one vast, continuous space containing all matter and energy. Scientists did not yet talk seriously about the possibility of other universes. The term universe still referred to the totality of existence, but that totality was becoming more dynamic, more complex, and crucially, more open to deeper questions. One such question concerned the uniformity of the cosmos. As astronomers looked deeper into space, they noticed that the universe appeared remarkably smooth and consistent. The cosmic microwave background, radiation left over from the early universe, was nearly the same in all directions. This uniformity required explanation. How could distant regions of the universe, too far apart to have exchanged information since the Big Bang, appear so similar? This puzzle set the stage for the next major development, the theory of cosmic inflation. In the early 1980s, physicist Alan Guth proposed that in the first fraction of a second after the Big Bang, the universe underwent a brief but enormous burst of expansion. This inflation would smooth out the universe and explain its uniformity, but it also introduced something new, an idea with far-reaching implications. Inflation, it turns out, does not necessarily stop everywhere at once. In some regions, it could end, creating bubble universes like ours. In others, it might continue. This leads to a picture of eternal inflation, where countless universes could be forming in a vast, inflating background. But before that idea could take hold, scientists had to first understand inflation itself and its role in shaping the cosmos we observe. The early universe, once thought to be a singular event, now hinted at something far stranger and more expansive. The notion that our universe might not be the only one did not come from speculation. It emerged slowly and reluctantly from attempts to solve real problems in cosmology. Each step, from Einstein's equations to Hubble's redshifts, built toward a new picture of reality, a picture in which the universe might be just one piece of a much larger structure. This realization, that the universe had a beginning and was not eternal, set the stage for one of the most important observational breakthroughs in the history of science. The story of an expanding universe did not begin in a laboratory or with a single experiment, but with a telescope pointed toward the stars and the work of one astronomer who would unknowingly reshape modern cosmology. In the late 1920s, Edwin Hubble was working at the Mount Wilson Observatory in California, home to the Hooker telescope, which at the time was the largest in the world. Hubble had a keen interest in the nature of spiral nebulae, faint, cloudy objects visible in the night sky. There was ongoing debate about what these objects really were. Were they part of our Milky Way galaxy, or were they island universes of their own, galaxies far beyond our own? To answer this, Hubble studied Cepheid variable stars, pulsating stars that could be used as distance markers thanks to their known relationship between brightness and pulsation rate. Using these stars as standard candles, Hubble measured the distance to several spiral nebulae and made a decisive discovery. They were much farther away than the boundaries of the Milky Way. These nebulae were not local clouds of gas, they were galaxies, vast collections of stars, like our own, scattered throughout space. This alone was a transformative insight. It revealed that the universe was far larger than previously imagined. But what Hubble did next would be even more revolutionary. Building on the earlier work of Vesto Slipher, who had been measuring the redshifts of galaxy spectra since the 19-teens, Hubble combined these redshift measurements with his distance calculations. When he plotted the velocities of galaxies, how fast they were moving away from Earth, against their distances, he noticed a remarkable pattern. The farther away a galaxy was, the faster it seemed to be receding. In 1929, Hubble published this result. The relationship he uncovered became known as Hubble's law. In simple terms, the universe was expanding, and it was doing so uniformly in all directions. this expansion did not mean galaxies were flying through space away from some central point. Rather, space itself was stretching, carrying galaxies along with it. A common analogy is that of a balloon with dots drawn on its surface. As the balloon inflates, the dots move away from each other, not because they are moving themselves, but because the surface between them is expanding. Hubble's discovery provided direct observational evidence that supported the theoretical predictions emerging from general relativity. As mentioned earlier, Einstein's original equations implied a dynamic universe, either expanding or contracting. Hubble's data made it clear the universe was expanding. Einstein, upon learning of Hubble's results, reportedly visited Mount Wilson to meet Hubble in person and view the telescope. Afterward, Einstein acknowledged that the cosmological constant he had added to keep the universe static might have been unnecessary. Though he later explored uses for the constant in different contexts, his encounter with Hubble marked a pivotal moment in reconciling theory with observation. The implications of an expanding universe were profound. If space is expanding now, then it must have been more compact in the past. Rewinding that expansion leads to a moment when the universe began, a finite point in time when all matter, energy, space, and even time itself were condensed into an incredibly hot, dense state. This concept became the foundation of what would later be known as the Big Bang theory, though the name itself was coined sarcastically by British astronomer Fred Hoyle, who was skeptical of the idea. Hoyle favored a steady-state model in which the universe had no beginning or end in time, but as observational evidence continued to mount, particularly with the discovery of the cosmic microwave background radiation in the 1960s, the Big Bang model gained overwhelming support. But returning to Hubble's era, it is important to understand that while his discovery confirmed the expansion of the universe, it did not yet tell scientists why the expansion was happening or what mechanism drove it. That question would remain open for several more decades, leading physicists to explore new theories of the early universe and, eventually, the possibility of cosmic inflation. Still, Hubble's work had fundamentally changed the scale and shape of our cosmological understanding. The universe was no longer a static stage, but a dynamic, evolving structure. The distances involved were staggering. Galaxies were not just scattered nearby, they were billions of light-years away. Each one contained hundreds of billions of stars, and there were billions of such galaxies. This expansion was not just a curiosity, it was a clue, a trailhead leading to the origins of the universe, to its earliest moments, and to questions that had never before been asked in the realm of physics. The institutional backdrop of Hubble's research was also worth noting. The Carnegie Institution for Science, which funded the Mount Wilson Observatory, provided the tools and support for this groundbreaking work. Advances in telescope engineering, spectroscopy, and photographic techniques all played a role in allowing astronomers to see farther and more clearly into space than ever before. As the expansion of the universe became widely accepted, it reshaped other fields of science as well. In astrophysics, it led to new models of star and galaxy formation. In particle physics, it opened the door to thinking about high-energy conditions in the early universe. And in philosophy, it reopened ancient questions about beginnings, creation, and the nature of time. But perhaps most importantly for our story, the expanding universe revealed that the cosmos was not a closed system of eternal sameness. It had structure, it had a past, and if it had a beginning, it might have alternatives. That is where the seeds of the multiverse idea were planted, not in speculative fiction, but in precise measurements of galaxies and light. It is easy to forget how controversial these ideas once were. At the time of Hubble's announcement, many scientists resisted the idea of a beginning to the universe. It seemed to edge too closely to metaphysical or theological concepts. But science, grounded in observation, began to follow the data wherever it led, and where it led was to a new vision of the cosmos, one that was larger, older, and more dynamic than anything previously imagined. Hubble's findings also forced scientists to think statistically. If the universe is expanding everywhere, then there is no special center, no privileged vantage point. This principle, known as the cosmological principle, holds that the universe is homogeneous and isotropic on large scales. In other words, it looks roughly the same in all directions and from any location. That principle would become essential for later developments in cosmology, particularly when thinking about what lies beyond our observable horizon. If our universe looks like this here, might other regions look different? Might the laws of physics themselves vary across space or in other domains beyond our reach? These questions, which once would have seemed speculative, began to gain traction. Not because scientists were looking for multiple universes, but because the structure of this one demanded deeper explanation. As scientists began to accept that the universe was expanding and had a beginning, attention naturally turned to its earliest moments. If the Big Bang marked the birth of the universe, what exactly happened in the first fractions of a second after that event? The answers to those questions, it turned out, would lead to one of the most revolutionary ideas in modern cosmology, a theory known as cosmic inflation. In the late 1970s, physicists working on problems in particle physics and cosmology began noticing something puzzling about the structure of the universe. Observations showed that the universe was remarkably uniform on large scales. The temperature of the cosmic microwave background radiation, which is the leftover glow from the early universe, was almost exactly the same in every direction. There were only tiny fluctuations, on the order of 1 part in 100,000. This smoothness was not easy to explain. According to the standard Big Bang model, regions of space that are now widely separated, so distant that light could not have traveled between them in the time since the Big Bang, should not be able to coordinate their properties. In other words, they were too far apart to have ever communicated with one another, and yet they appeared to have the same temperature, density, and structure. This became known as the horizon problem, and it pointed to something missing in the standard cosmological picture. There were other issues as well, such as the flatness problem. Measurements indicated that the universe was geometrically flat, meaning that parallel lines remain parallel even at cosmic scales. But a flat universe is not a stable configuration. It requires extremely fine-tuned conditions in the early universe, so fine-tuned that it seemed unlikely to be mere coincidence. Enter Alan Guth, a young physicist at the time, working at the Stanford Linear Accelerator Center. Guth was interested in applying ideas from particle physics to cosmology. In particular, he was studying phase transitions in the early universe, moments when the universe might have shifted from one state to another, similar to how water freezes into ice or boils into steam. In 1980, Guth proposed a bold solution. He suggested that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of rapid, exponential expansion. This expansion was not gradual, it was sudden and violent, increasing the size of the universe by an enormous factor in an unimaginably short time. He called this process inflation. According to Guth's theory, during this inflationary epoch, space itself expanded faster than the speed of light. This may sound like a violation of Einstein's theory of relativity, but it is not. Relativity prohibits objects from moving through space faster than light, but it does not limit how fast space itself can expand. Inflation allowed regions that were once close together and in thermal equilibrium to be pushed far apart. This explained the uniform temperature across the universe. Those regions had once been in contact before inflation stretched them beyond each other's horizons. Inflation also addressed the flatness problem. The rapid expansion would have stretched any initial curvature of space so much that it would now appear flat, just as the curved surface of a balloon can appear flat when viewed up close. The theory was elegant and compelling, but it raised new questions. For instance, what caused inflation to start and what made it stop? To answer these, Guth introduced the idea of a false vacuum, a high-energy state of space that is unstable. During inflation, the universe is trapped in this false vacuum, which has a kind of built-in energy that drives the exponential expansion. Eventually, this vacuum decays into a more stable state, releasing energy that reheats the universe and sets off the chain of events we associate with the traditional Big Bang model. While Guth's initial version of inflation had problems, specifically with how inflation ends uniformly across space, it sparked intense interest and further development. One of the key refinements came from Russian physicist Andrei Linde. In the early 1980s, Linde proposed what he called new inflation and later chaotic inflation. His models solved some of the issues in Guth's original proposal and offered a more robust mechanism for how inflation could occur in different regions of space. What made inflation so powerful as a scientific theory was not just its ability to solve existing problems, it also made predictions that could be tested. It predicted that the universe should be nearly flat, that there should be a spectrum of density fluctuations in the early universe, and that these fluctuations should have specific statistical properties. In the decades that followed, satellite missions like COBE, JW-MAP, and Planck collected precise data on the cosmic microwave background radiation. These observations matched the predictions of inflation with remarkable accuracy. Inflation had gone from a theoretical fix to a cornerstone of modern cosmology, but it did something else too, something unexpected. It hinted at the possibility that our universe might not be the only one. Here is how. In some versions of inflation, especially Linde's chaotic inflation, the process does not stop everywhere at once. Instead, inflation ends in some regions, creating pockets of space where the energy of the false vacuum has decayed. These pockets become what we would call universes, regions with their own local physics, expanding and evolving independently. But in other regions, inflation continues. It keeps stretching space, generating more and more of these pockets. This leads to a concept known as eternal inflation. In eternal inflation, the process of universe creation never ends. The overall space continues inflating forever, and within it, individual universes like ours bubble into existence. Each of these bubbles could have different properties, different physical constants, even different laws of physics, depending on how the false vacuum decays in that region. This is where the multiverse enters serious scientific discussion. The idea that there might be other universes is not a philosophical add-on to inflation. It is a consequence of the mathematics, a prediction of how inflation naturally operates under certain conditions. Eternal inflation suggests that what we call the universe is just one bubble in an endlessly growing foam. The observable universe, the part we can see, is only a tiny fragment of a much larger and more diverse cosmic landscape. Importantly, this multiverse is not just a convenient speculation. It arises from theories that have already been successful in describing the world we observe. That is why cosmologists began taking the idea seriously, not because they wanted to believe in other universes, but because the logic of inflation led them there. Of course, eternal inflation also raises deep questions. If other universes are forever out of reach, how could we ever test their existence? What counts as science if the phenomena in question can never be observed? These are not minor concerns. They strike at the very heart of what it means to do science. Yet many physicists argue that just because something is hard to test does not mean it is unscientific, especially if it emerges naturally from theories that are otherwise well supported. Alan Guth once described inflation as the ultimate free lunch. It offers a mechanism by which the universe could emerge from almost nothing, no matter, no structure, just the quantum fields of space. With eternal inflation, the meal is never over. The universe keeps creating more and more versions of itself. Once the idea of cosmic inflation had taken root, it quickly became clear that its consequences stretched far beyond explaining the smoothness and flatness of the observable universe. The refined models of inflation did not just describe what happened in our universe. They hinted at a much larger structure, one in which our universe might be only a single bubble in an endlessly growing sea of space. This idea, known as eternal inflation, led scientists to one of the most provocative possibilities in modern physics, the creation of baby universes. The concept of eternal inflation was not present in Alan Guth's original formulation. His model assumed that inflation ended quickly and uniformly across the universe, followed by the hot Big Bang and the standard cosmic evolution. But in the early 1980s, Russian physicist Andrei Linde proposed a more flexible version of inflation. In his chaotic inflation model, inflation was not a neatly coordinated process. It did not require a perfectly smooth beginning or finely tuned conditions. Instead, quantum fluctuations, tiny random changes in the energy of space, could trigger inflation in some regions even while it ended in others. This meant that the inflationary process could become self-replicating. Imagine space as a boiling pot of water. Bubbles form, grow, and rise to the surface. In a similar way, inflation causes regions of space to bubble out into new universes. Each bubble forms when inflation ends in that region, releasing energy and allowing matter to form. But surrounding the bubble, inflation continues. New bubbles continue to form, each disconnected from the others, each with its own local properties and history. This is the central idea behind eternal inflation. The larger background space never stops inflating. It stretches exponentially, creating more volume and more opportunities for new bubbles to emerge. This process goes on indefinitely. As a result, the cosmos is not a single universe, but a multiverse, a vast and growing collection of bubble universes, each born from its own patch of inflating space. Andre Linde described this scenario in vivid terms. He imagined a multiverse eternally reproducing itself, with each bubble potentially giving rise to further inflation in its own right. In this view, the multiverse is a kind of fractal structure, complex, layered, and endlessly branching. The observable universe, the part we can see and measure, is just one of these bubbles. There could be countless others, forever beyond our observational reach. One of the striking aspects of eternal inflation is how naturally it arises from the physics of quantum fields. In these models, inflation is driven by a scalar field, a kind of energy field that fills space. This field is subject to quantum fluctuations, which cause different regions of space to roll down the field's energy potential at different rates. Some regions reach the end of inflation quickly, others linger in a high-energy state, where inflation continues. Because space itself is expanding during this process, the volume of the inflating region grows faster than inflation can end. In this way, inflation becomes eternal into the future. The mathematics of eternal inflation suggest that this process is not just possible, but inevitable under certain conditions. Once it starts, it never stops. There is always some part of space still inflating, always more baby universes being born. Each of these baby universes may have different properties. The laws of physics we observe in our universe, such as the strengths of fundamental forces, the masses of elementary particles, or the nature of dark energy, could be local features, not universal ones. In other words, the multiverse created by eternal inflation could contain regions with different physical laws. This has enormous implications. It means that the laws of physics might not be uniquely determined by fundamental principles. Instead, they might be environmental, a product of where in the multiverse we happen to live. Our universe is the way it is because it is one bubble among many, and its particular properties are compatible with the emergence of life and observers. This is where the concept of the anthropic principle enters the discussion, which we will explore more deeply in a later section. But before turning to philosophy, it is worth emphasizing how eternal inflation emerged not as an exotic add-on to physics, but as a straightforward consequence of the models already in place. Linde, Guth, and others were not trying to invent multiple universes. They were trying to understand why this universe looks the way it does, and the mathematics pointed to a much larger, more diverse structure than anyone had originally imagined. The idea of bubble universes also led to a re-examination of what we mean by the word universe. Traditionally, it referred to everything that exists, but in the context of eternal inflation, universe takes on a more local meaning. A single, causally connected region with its own space-time, its own matter, and its own laws. The collection of all these universes becomes the multiverse. This raises challenging questions about observability. If other bubbles are beyond our horizon, too far away for light or any signal to ever reach us, how can we know they exist? Can we test eternal inflation? Can we confirm the existence of the multiverse? These are not trivial issues. Science is built on observation and experiment. If eternal inflation predicts entities that can never be observed, does it still count as science? Many physicists argue that it does, as long as the theory makes testable predictions about our own universe. And inflation does exactly that. It explains the flatness of space, the uniformity of the cosmic microwave background, and the spectrum of density fluctuations that seeded galaxies. In this sense, eternal inflation earns its place in scientific discourse by being part of a larger predictive framework. Even if we cannot observe other bubbles directly, we can assess the theory that predicts them by checking its consequences in our own observable patch. Some physicists have proposed indirect ways to search for evidence of other bubble universes. For example, if two bubbles collided in the early stages of formation, they might leave a detectable imprint in the cosmic microwave background, a circular pattern or temperature anomaly. So far, no definitive evidence of such a collision has been found, but the search continues. Others have pointed out that eternal inflation might provide a natural explanation for the seemingly fine-tuned nature of our universe. Instead of requiring a special explanation for why the constants of nature are so perfectly balanced to allow life, eternal inflation suggests that all possible combinations are realized somewhere in the multiverse. We happen to live in a region where conditions are right for life, simply because regions where conditions are not right have no observers to ask the question. While this explanation remains controversial, it highlights how eternal inflation connects cosmology, quantum physics, and deep questions about existence. It is not just a theory about the origin of space, it is a framework that reshapes our understanding of reality itself. The development of eternal inflation also brought renewed attention to the relationship between physics and mathematics. The equations that describe quantum fields and inflationary dynamics are abstract, yet they describe a process that may be creating entire universes. This connection between the mathematical and the physical raises profound philosophical questions, some of which would later be explored in even more speculative proposals, such as the mathematical universe hypothesis. But even without venturing into those territories, eternal inflation alone represents a turning point in cosmology. It is a moment when the focus shifts from the story of our universe to the story of all possible universes. From a single cosmic history to an ensemble of histories, each unfolding in its own bubble, each forever beyond the reach of the others. While the inflationary multiverse emerges from the physics of the very large, there is another pathway to multiple universes that comes from the physics of the very small. In fact, long before the idea of eternal inflation began to take shape, the foundations of quantum mechanics had already suggested a radically different vision of reality, one where every outcome of every quantum event actually happens, each in its own separate branch of the universe. To understand how this idea came about, we have to return to the early 20th century, when a group of physicists began developing a new theory to describe the behavior of particles at atomic and subatomic scales. This theory, quantum mechanics, quickly became one of the most successful frameworks in all of science. It accurately predicted the behavior of electrons in atoms, the properties of chemical bonds, and even the functioning of semiconductors and lasers. But it also introduced deep conceptual puzzles. At the heart of quantum mechanics is the principle of superposition. This means that a quantum system, such as an electron, can exist in multiple states at once. For example, an electron can be in a state where it is both spinning clockwise and counterclockwise, or located in two different places until it is measured. Only when we observe the system does it appear to choose one definite outcome. This leads to the famous thought experiment known as Schrödinger's cat. Imagine a cat placed in a sealed box along with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of the poison, killing the cat. If the atom does not decay, the cat remains alive. According to quantum mechanics, until the box is opened and the system is observed, the atom exists in a superposition of decayed and undecayed states. Therefore, the cat is both alive and dead at the same time, at least in theory. Physicists were troubled by this interpretation. The standard explanation, known as the Copenhagen interpretation, held that the wave function, a mathematical description of the quantum state, collapses into a single outcome when measured. But this raised a question. What counts as a measurement? Does a particle somehow know when it is being observed? And why should an observer be necessary to determine physical reality? In 1957, a young physicist named Hugh Everett III proposed an alternative view. Instead of wave function collapse, Everett suggested that the wave function never collapses at all. Every possible outcome of a quantum measurement actually occurs, but each in a separate, non-interacting branch of reality. This became known as the many worlds interpretation of quantum mechanics. In Everett's view, when a quantum event happens, say an electron is measured to be in one of two states, the universe splits into two branches. In one branch, the electron is found in state A. In the other, it is found in state B. Both outcomes are real, but they occur in separate parallel worlds that evolve independently. This interpretation removes the need for a special role for observation or measurement. It treats the wave function as a complete and objective description of reality, and it applies the rules of quantum mechanics to everything, including observers themselves. There is no collapse. Instead, there is branching. At the time, Everett's idea was largely ignored. The physics community was more comfortable with the Copenhagen interpretation, which, while philosophically fuzzy, had been effective in guiding experiments. Everett, disillusioned by the reception of his work, left academia and went on to a career in military research. But the many worlds interpretation did not disappear. It was revived in later decades by physicists such as Bryce DeWitt, who helped popularize the term many worlds and explored its implications for quantum cosmology. Gradually, the idea began to gain respect among physicists and philosophers who valued its consistency and avoidance of arbitrary rules like wave function collapse. One of the strengths of the many worlds interpretation is that it requires no changes to the formalism of quantum mechanics. It simply takes the mathematics seriously and at face value. If the equations say a system can exist in multiple states, then all of those states exist. The branching of universes is not an added hypothesis. It is a consequence of the theory's evolution over time. This branching does not happen just on rare occasions or in special labs. According to the many worlds view, branching is happening constantly all around us. Every time a quantum event occurs with multiple possible outcomes, every time a photon bounces off a molecule in your eye, or an atom transitions between energy levels, the universe splits. The number of branches grows exponentially, leading to an unimaginably vast multiverse of parallel realities. Importantly, these branches are not alternate timelines in the science fiction sense. They do not communicate or interfere with each other. Once the branching occurs, each version of reality becomes causally isolated. From the perspective of someone inside one branch, the other branches are inaccessible. You can never travel between them, or even detect their existence directly. This raises philosophical questions as well as scientific ones. If all outcomes happen, then what does probability mean? When we say that a quantum event has a 50-50 chance of one result or another, what are we really saying in a framework where both outcomes definitely occur? In the many worlds view, probability is reinterpreted in terms of the relative weight or amplitude of different branches, a subtle and ongoing topic of debate in the philosophy of physics. Critics of many worlds argue that it multiplies entities beyond necessity, that it invokes an ever-growing collection of universes without empirical evidence. Supporters reply that the interpretation is actually more parsimonious because it removes the need for ad hoc mechanisms like wave function collapse. It is not adding new physics, but rather taking existing physics seriously. Some have even speculated about possible experimental tests of many worlds, though these ideas remain speculative. For now, the interpretation stands as one of several competing ways to understand quantum mechanics. Others include the de Broglie-Bohm pilot wave theory, objective collapse models, and relational quantum mechanics. None has yet achieved a definitive edge in terms of experimental validation. Still, many worlds has had a profound impact on how physicists think about reality. It reframes the universe not as a single unfolding chain of events, but as an ever-branching tree of possibilities. In this view, the multiverse is not a distant consequence of cosmology, but a direct implication of the quantum laws that govern every particle, every atom, every interaction. This interpretation also blurs the line between physics and philosophy. What does it mean for something to be real if it cannot be observed? Can we meaningfully talk about other versions of ourselves existing in parallel branches? Are all possible histories equally valid? Some physicists, such as David Deutsch and Sean Carroll, have argued strongly in favor of the many worlds interpretation. They see it as the most natural and consistent way to understand quantum theory. Carroll has written that every version of you that could exist does exist, and that this view brings coherence to the theory without introducing artificial boundaries between quantum and classical worlds. Others remain more cautious. They point out that the interpretation, while elegant, makes no distinct predictions that would allow it to be experimentally distinguished from other interpretations. Until such a test is found, the many worlds view remains a compelling but unproven framework, one among several ways to make sense of the strange and beautiful mathematics of the quantum world. As the many worlds interpretation of quantum mechanics reframed our understanding of reality at the smallest scales, another movement was underway in theoretical physics, one aimed at unifying all of nature's fundamental forces into a single coherent framework. That effort led to string theory, a bold and mathematically rich proposal that did more than seek a theory of everything. It also introduced a new kind of multiverse, one not based on cosmic inflation or quantum branching, but on the vast number of possible solutions to the equations of the theory itself. The story of string theory began in the late 20th century as physicists attempted to reconcile two powerful but seemingly incompatible theories: general relativity, which describes gravity and the structure of space and time, and quantum field theory, which governs the behavior of particles and the other three forces of nature: the electromagnetic, strong nuclear, and weak nuclear forces. These two pillars of physics had both passed every experimental test within their respective domains, but they resisted every effort to merge them into a single, consistent theory. Attempts to quantize gravity, treating it in the same way as other forces, ran into serious mathematical problems. The equations became uncontrollably infinite, and predictions lost their meaning. What physicists needed was a deeper framework, one that would naturally include both gravity and quantum mechanics. String theory emerged as a candidate for such a framework. Its central idea is simple but revolutionary. Instead of treating particles like electrons and quarks as zero-dimensional points, string theory proposes that these particles are actually tiny, vibrating one-dimensional loops, or strings. Each type of vibration corresponds to a different particle. A string vibrating one way might appear as a photon. A different vibration could produce a graviton, the hypothetical quantum particle of gravity. One of the key virtues of string theory is that it naturally includes gravity. Unlike earlier quantum field theories, which struggle with the infinite energies of gravitational interactions, string theory smooths out those infinities by replacing point particles with extended strings. This makes gravity not only compatible with quantum mechanics, but an inevitable part of the theory. However, string theory comes with unusual mathematical requirements. To be consistent, it demands more dimensions than the four we experience: 3 of space and 1 of time. In most versions, the theory requires 10 spatial dimensions and 1 time dimension. Since we do not observe these extra dimensions in everyday life, the theory proposes that they are compactified, curled up into tiny shapes too small to detect directly. This is where things become both fascinating and complicated. There are many different ways to curl up these extra dimensions. Just as a piece of paper can be folded in countless ways, the extra dimensions of string theory can take on a huge variety of geometric forms. Each configuration produces a different version of physics in the resulting 4-dimensional world: different particles, different forces, even different values for the fundamental constants of nature. This led to what is now called the landscape problem in string theory. Instead of predicting one unique universe, string theory appeared to allow an enormous number of possible universes. Estimates vary, but many physicists believe there are on the order of 10 raised to the 500th power possible solutions. That is a 1 followed by 500 zeros, a number so large it defies human comprehension. Each of these solutions represents a different way to compactify the extra dimensions and stabilize the energy of the vacuum. Each one corresponds to a different low-energy physics, meaning a different set of laws governing particles and forces. From our perspective, each solution is a different possible universe. This created a dilemma. If string theory allows such a vast number of possible universes, how do we explain why we live in this one? Why do we observe this set of particles, this set of forces, and this set of constants? In traditional physics, a good theory is expected to make unique predictions. If a theory allows too many possibilities, it risks losing its explanatory power. Critics of string theory argued that the theory was not predictive enough, that it could be used to explain almost anything, and therefore explained nothing. Supporters responded that this vast landscape of solutions might not be a flaw, but a feature. Perhaps nature does allow for many different universes, and we happen to live in one that supports complex structures, chemistry, and life. This argument connected naturally with the idea of a multiverse produced by eternal inflation. If inflation creates many different bubble universes, and string theory describes many possible vacuum states, then perhaps each bubble ends up in a different part of the string theory landscape. This synthesis of ideas gained momentum in the early 2000s, particularly with the work of physicists such as Leonard Susskind and Raphael Bousso. They proposed that eternal inflation could populate the string theory landscape, creating a multiverse in which all possible combinations of physical laws are realized somewhere. In this view, the apparent fine-tuning of our universe, the precise values of the constants that allow stars to shine, atoms to form, and life to exist, does not require a special explanation. It is simply a matter of selection. Among the vast ensemble of possible universes, we find ourselves in one of the few where conditions allow observers to evolve and ask these questions. This application of the anthropic principle is not universally accepted. Many physicists remain skeptical of using anthropic reasoning as a scientific tool. They argue that it lacks predictive power and borders on circular logic. Others see it as a reasonable way to deal with the consequences of a theory that, for better or worse, allows a huge diversity of outcomes. Importantly, the string theory landscape is not something invented to support the multiverse. It is an unavoidable consequence of the theory's internal mathematics. Physicists did not set out to find a multiverse. They found themselves facing one because the equations of string theory pointed to it. Still, the landscape has changed how physicists approach the idea of a final theory. Instead of expecting one unique solution that describes our universe, they now consider the possibility that fundamental theory provides a vast menu of possibilities and that selection occurs through cosmological processes. This idea also led to new questions about how physics can be tested. If different universes have different laws and we can only observe one, how can we know whether the theory is true? One approach is to look for indirect evidence. For example, predictions about the types of particles we might find in high-energy experiments, or the behavior of gravity at small scales. Another approach is to look for consistency. Does the theory explain known physics in our universe, and does it do so more elegantly or completely than alternatives? At the same time, research continues into the mathematical structure of string theory itself. Physicists are exploring dualities, relationships between seemingly different theories that turn out to describe the same underlying physics, and trying to understand how the landscape is shaped and constrained. Some believe there may be principles yet undiscovered that select certain vacua over others, narrowing the field and restoring some measure of predictability. Others have proposed alternatives to string theory, such as loop quantum gravity, that take different approaches to unifying physics. But for now, string theory remains the leading candidate for a theory that includes both quantum mechanics and gravity. What is remarkable is that string theory, a theory originally developed to explain particle interactions, ended up revealing a cosmic structure of almost unimaginable scope. A multiverse not of space-time bubbles, but of mathematical possibilities, a library of potential universes, each with its own internal logic. And so, through the mathematics of higher dimensional geometry and the challenges of unifying the forces of nature, physics found itself once again confronting the possibility that our universe might be only one among many. As physicists grappled with the vast range of possible universes allowed by string theory, a deeper question emerged, one that had quietly lingered in scientific and philosophical circles for decades. Why does our universe appear so perfectly tuned for life? This was not a question of spiritual intent or metaphysical design, but one grounded in physics. The laws of nature, the constants that govern them, and the initial conditions of the cosmos all seemed to fall within remarkably narrow ranges. Ranges that, if altered even slightly, would make the emergence of life and even matter itself impossible. This observation led to what is known as the fine-tuning problem. Physicists began noticing that certain parameters in the equations of nature appeared to be delicately balanced. If the strength of gravity were even a little weaker, stars might never form. If it were slightly stronger, stars might burn out too quickly or collapse into black holes. If the electromagnetic force were just a bit different, atoms might not hold together. And if the strong nuclear force were stronger or weaker by just a few percent, the processes that build heavier elements inside stars would not work. One striking example is the mass difference between the neutron and the proton. If that difference were just slightly larger or smaller, hydrogen would be unstable, or fusion in stars would never ignite. Similarly, the cosmological constant, the term in Einstein's equations that represents the energy density of empty space, is observed to have a small but non-zero value. If it were even 100 times larger, the universe would have expanded too quickly for galaxies to form. These and many other examples seem to suggest that our universe was just right in ways that were hard to explain purely through chance or necessity. For some, this raised the unsettling possibility that our universe was special in a way that demanded explanation beyond the usual boundaries of physics. One possible response came in the form of the anthropic principle. First proposed by physicist Brandon Carter in the early 1970s, the anthropic principle comes in several versions, but its core idea is simple. Any valid theory of the universe must be consistent with the existence of observers like us. In other words, we should not be surprised to find that the universe allows life, because if it did not, we would not be here to ask the question. At first glance, this may sound like a tautology or even an evasion of deeper inquiry, but the anthropic principle becomes more meaningful when placed within the context of the multiverse. If there is only one universe, then its fine-tuning might seem improbable or even miraculous. But if there are many universes, perhaps an enormous or even infinite number, each with different physical laws or constants, then it becomes more plausible that at least some of them would support life. In such a scenario, we find ourselves in a life-permitting universe not because it was designed or specially chosen, but simply because it is one of the rare regions where observers can exist. We are the product of selection bias, shaped not by chance alone, but by the requirement that we must be in a universe where life is possible. This idea gained prominence in the late 20th century, particularly through the work of physicists like Steven Weinberg. In the 1980s, Weinberg applied anthropic reasoning to the cosmological constant problem. He argued that if the value of the cosmological constant were randomly distributed across different universes in a multiverse, then we should expect to observe a value just low enough to allow the formation of galaxies, because otherwise observers would not be able to exist. Remarkably, this prediction was made before the cosmological constant was observed to be small but non-zero, a fact that some see as evidence in favor of anthropic reasoning. Of course, the anthropic principle remains controversial. Some physicists worry that it undermines the predictive power of science. If we can always explain observations by saying, "We observe it this way because otherwise we would not be here," then how can we ever falsify a theory? Others argue that the anthropic principle is not an explanation in itself, but rather a filter that helps guide which kinds of explanations are worth considering. Yet when combined with eternal inflation and the string theory landscape, the anthropic principle becomes part of a larger scientific framework. It offers a way to understand why certain physical constants have the values they do, not by deriving them from first principles, but by recognizing that they may vary across a vast ensemble of universes. This shift from uniqueness to multiplicity is a profound change in how we think about the laws of nature. For centuries, science sought a single, elegant set of laws that uniquely determined the structure of the universe. But if the multiverse is real, then many of those laws might be local, not universal. They might emerge from the geometry of compactified dimensions, the vacuum state of a particular region, or the outcomes of symmetry breaking in the early universe. In this new view, our universe is not the only possible one. It is just one of many, and its particular features, including those that make life possible, are not surprising. They are simply part of the subset of universes where life can arise. This perspective has also influenced the way cosmologists think about probability. In a multiverse, the question is not, why is the universe like this, but, given a distribution of universes, how likely is it that one would look like ours? This has led to efforts to define a measure problem, a way to count or weigh different universes and determine how common or rare certain properties might be. But this task is far from easy. The multiverse, by its nature, includes regions that may be infinite in number or extent. Trying to calculate probabilities in such a setting leads to deep mathematical and conceptual challenges. Different measures can lead to different conclusions, and there is no consensus yet on which approach is correct. Nonetheless, the anthropic principle and fine-tuning arguments continue to play a central role in the debate over the multiverse. They provide motivation for taking the multiverse seriously, not as a metaphysical speculation, but as a scientific response to real puzzles about the structure of the universe. Critics still push back, noting that these ideas depend heavily on assumptions that cannot be directly tested. The existence of other universes, the variation of physical constants across them, and the nature of the multiverse as a whole remains speculative. And while the anthropic principle may help explain why the universe permits life, it says little about the origin of the multiverse or the deeper mechanisms that govern it. Still, many physicists and philosophers find the anthropic perspective compelling. It offers a way to navigate the fine-tuning problem without invoking design or coincidence. And it ties together several strands of modern physics, from inflation to string theory, in a conceptually coherent, if philosophically challenging, framework. In this way, the multiverse is not simply a hypothesis about space. It is a response to questions of necessity and contingency. It reframes the search for a fundamental theory of nature, suggesting that the ultimate answer may not be a unique set of equations, but a vast ensemble of possibilities, with our universe as one realized outcome among many. As the anthropic principle and the multiverse landscape stirred both intrigue and controversy, another, more fundamental issue lingered quietly in the background, one that cuts to the very heart of cosmology itself. Even if other universes exist, can we ever detect them? Can we, in principle or in practice, observe or measure anything beyond our own cosmic domain? This question brings us face to face with the concept of the cosmic horizon, a boundary not made of matter or energy, but of the limits of observation imposed by the nature of space, time, and light itself. To understand the cosmic horizon, we begin with a simple fact: light takes time to travel. When we look into space, we are also looking back in time. The light from the moon takes about 1 second to reach Earth. The light from the sun takes about 8 minutes. When we look at distant galaxies, we are seeing them not as they are now, but as they were millions or even billions of years ago. Because the universe has a finite age, around 13¾ billion years, and because the speed of light is finite, there is a maximum distance from which light could have reached us since the beginning of the universe. That distance defines our observable universe. It is not a physical wall or edge, but rather a limit to how far we can see. Beyond that horizon, space continues. Galaxies and matter may exist. Indeed, according to our best cosmological models, they almost certainly do, but their light has not had time to reach us. And due to the expansion of space, some regions are receding from us faster than light. Their signals will never reach us, no matter how long we wait. This boundary has profound implications. It means that all of our observations, all of our measurements, all of our theories about the universe are based on a sample, a vast one to be sure, but still only a portion of the total cosmos. What lies beyond the observable universe is, by definition, unobservable. It exists outside our light cone and will remain permanently inaccessible. This introduces an important distinction between the universe and the observable universe. The observable universe is what we can study. It is bounded by our cosmic horizon. The full universe may be much larger, possibly infinite, but its extent is unknown and perhaps unknowable. In everyday cosmology, scientists work under the assumption of the cosmological principle that the universe is homogeneous and isotropic on large scales. This means that it looks roughly the same in all directions and from all locations. The principle is not something we can prove in full, because we cannot travel to other parts of the universe to verify it. But the observable evidence, especially the smoothness of the cosmic microwave background, strongly supports it. Still, the horizon imposes a kind of epistemic humility. There may be structures, phenomena, or even entire realms of existence beyond our horizon that we can never access. The laws of physics might vary outside our cosmic patch. Other regions might have different constants, different symmetries, different histories. This is where the discussion of the multiverse intersects with the limitations of observation. Eternal inflation, the string landscape, and the many worlds interpretation of quantum mechanics all suggest that other universes or regions of space may exist. But if those regions are causally disconnected from us, if no signal from them can ever reach us, can they be said to be part of the scientific enterprise? Some physicists argue that they can, as long as the overarching theory that predicts them also makes testable predictions within our observable universe. For example, inflation predicts certain statistical properties of the cosmic microwave background, which we have measured with great precision. If those predictions are confirmed, the theory gains credibility, even if some of its consequences lie beyond observation. Others are more skeptical. They warn that allowing unobservable entities into science risks eroding its empirical foundations. They ask, where do we draw the line between scientific theory and speculative metaphysics? This tension is not new in the history of science. There have always been debates about what counts as observable. At one time, atoms were considered hypothetical because no one had seen them. The same was once true for black holes, quarks, and even gravitational waves. Over time, advances in technology and methodology turned many of these hypothetical entities into observable ones. But the cosmic horizon may represent a more permanent boundary. Unlike earlier limitations, which were technological or practical, the horizon is rooted in the geometry of space-time itself. It marks the limits of what any observer can, in principle, know. Some scientists have proposed that certain signatures might leak across this boundary. For example, if our bubble universe had collided with another in the early stages of inflation, it might have left a faint scar in the cosmic microwave background, a subtle, circular anomaly or cold spot. Searches for such signatures have been conducted using data from satellites like WMAP and Planck. So far, no definitive evidence has been found, though a few unexplained anomalies remain the subject of ongoing investigation. Another speculative idea involves so-called gravitational echoes, ripples in space-time that might carry imprints of other regions. But these ideas are highly theoretical and currently beyond the reach of our instruments. In some respects, the horizon problem is less about what exists and more about what can be known. It forces us to confront the boundaries of empirical science and to reflect on the nature of explanation itself. Is a theory less valid if some of its consequences are unobservable? Or does its value lie in its internal consistency and its ability to explain what we can see? Philosophers of science have weighed in on this issue. Karl Popper famously argued that scientific theories must be falsifiable. If a theory makes no testable predictions, it does not belong in the domain of science. But others have noted that even within physics, some theories become accepted because they unify ideas or make progress in understanding even before direct tests are available. In modern cosmology, the frontier lies precisely at this intersection between what we can observe and what the laws of physics seem to imply. The cosmic horizon reminds us that science is not only a tool for knowledge, but also a framework shaped by limitations. It shows us that our understanding is always partial, always provisional, always bounded by what light can bring us. And yet, even within those boundaries, we continue to probe the edges. We refine our models. We test our predictions, we ask sharper questions. The unobservable may be unreachable, but it is not irrelevant. It shapes our theories, guides our expectations, and challenges our assumptions. As we've seen, the boundaries of our observable universe pose profound limitations on what we can directly know, yet theoretical physics often finds its way around such walls, through logic, mathematics, and inference. One of the most surprising of these pathways leads not to the vastness of space, but to its extreme compactness. In the study of black holes, physicists have found not only puzzles about gravity and quantum mechanics, but also possible connections to the multiverse itself. Black holes are among the most extreme objects in the universe. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. The idea was first hinted at in the 18th century. But the modern theory of black holes emerged from Einstein's general relativity in the early 20th century. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. The result is a singularity, a point of infinite density surrounded by an event horizon, the boundary beyond which no information can return. For many decades, black holes were seen as purely gravitational objects. They were defined entirely by just a few characteristics: mass, electric charge, and spin. This simplicity gave rise to the phrase, "black holes have no hair," meaning they carry no information about the matter that formed them, no fingerprints, no traces, no clues. But in the 1970s, this picture began to change. Physicist Stephen Hawking, building on earlier work by Jacob Bekenstein, made a startling discovery. Using principles from quantum field theory in curved spacetime, Hawking showed that black holes are not completely black. Instead, they emit radiation due to quantum effects near the event horizon. This radiation, now known as Hawking radiation, causes black holes to slowly lose mass and eventually evaporate. This finding led to a deep paradox, one that still challenges physicists today. If black holes evaporate completely, what happens to the information about the matter that fell into them? According to quantum mechanics, information can never be destroyed. Every process, no matter how complex, must be reversible at the quantum level. But if a black hole vanishes and takes its contents with it, then that information seems to be lost forever. This is known as the black hole information paradox, and it forces a confrontation between general relativity and quantum theory. Two frameworks that have both proven enormously successful, but that appear to conflict in this extreme case. Some physicists propose that the information is preserved in subtle correlations within the Hawking radiation, while others argued that new physics might be required. Still others suggested that the information is not lost, but escapes into a new region of space-time altogether, a new universe birthed inside the black hole. This last idea was championed most notably by theoretical physicist Lee Smolin, who proposed a speculative but thought-provoking theory known as cosmological natural selection. According to this idea, black holes do not simply destroy matter. Instead, they act as cosmic wombs, generating new regions of space-time, new universes, on the other side of their event horizons. In this framework, each new universe might have slightly different physical parameters, depending on the state of the black hole that produced it. If certain combinations of physical constants lead to more black holes forming, then those universes will have more offspring. Over cosmic timescales, this would create a kind of natural selection among universes, favoring those that are good at making black holes. This is an audacious proposal, but it has a certain internal logic. It links the formation of black holes, well-established astrophysical phenomena, to the origin of new universes. It also provides a naturalistic mechanism for the apparent fine-tuning of our own universe. Perhaps our universe is one of many generations in a long line of cosmic reproduction, and it inherited physical laws that are particularly good at generating structure and collapse. Although the idea of black holes as cosmic seeds remains speculative, it resonates with other developments in theoretical physics. For instance, in certain models of quantum gravity, space-time is not a continuous fabric, but a discrete structure made up of tiny units, or quanta. In such models, the singularity inside a black hole might be replaced by a region of extreme but finite density, beyond which space-time continues. This could allow for a bounce rather than a true end, and such a bounce could lead into a new, expanding universe. There are also connections to ideas in string theory. In the framework known as the ADS-CFT correspondence, a duality discovered by Juan Maldacena in the late 1990s, black holes in a certain kind of curved spacetime can be described in terms of a lower dimensional quantum field theory on the boundary of that space. This has provided new tools for studying the information paradox and understanding how quantum information might be preserved. While these approaches differ in detail, they share a common theme. Black holes are not the dead ends they once seemed. They are dynamic quantum mechanical systems that may encode profound truths about the nature of space-time, information, and reality itself. Returning to the idea of the multiverse, black holes may offer a physical mechanism for its generation, not through inflation or quantum branching, but through gravitational collapse. If every black hole gives rise to a new universe, then the multiverse becomes a kind of cosmic family tree, with each branch representing a new realm of existence, connected through gravitational ancestry. This view invites us to reconsider the flow of causality on the largest scales. In our everyday experience, the universe begins with a bang and ends with a fade. But in this broader vision, universes give birth to other universes, each with its own arrow of time, its own laws, and its own possibilities. The boundaries between what we call this universe and another begin to blur, replaced by a richer and more dynamic picture. Of course, these ideas remain on the frontier of physics. There is, as yet, no direct observational evidence that black holes create new universes, nor a universally accepted theory of quantum gravity that can fully describe what happens inside a black hole. But the growing interplay between gravity, quantum information, and high-energy theory continues to push these questions forward. In the meantime, black holes have already reshaped our understanding of the universe. They have taught us that space and time can warp to the point of collapse, that quantum effects permeate even the darkest corners of the cosmos, and that information, the currency of quantum physics, is more resilient than we once imagined. Whether or not they truly spawn baby universes, black holes remain one of the most promising laboratories for testing the ideas that lead us toward a multiverse. They remind us that even the most compact and hidden regions of the cosmos may contain clues to its largest and most expansive structures. If black holes hint at the possibility of new universes through the collapse of matter, another line of inquiry looks outward, toward the earliest light in our universe, searching for traces of ancient events that may have involved other cosmic realms. This search centers on the cosmic microwave background, an extraordinary remnant from the birth of the universe that offers a detailed record of its early history. Within this faint afterglow, some scientists hope to find signs that our universe may have once collided with another. The cosmic microwave background, often abbreviated as CMB, was first discovered in the mid-20th century by Arno Penzias and Robert Wilson, who were investigating sources of background noise for satellite communication systems. What they found, quite by accident, was a faint, uniform radiation coming from every direction in the sky. This signal turned out to be the cooled remnant of the hot plasma that filled the universe roughly 380,000 years after the Big Bang. At that moment in cosmic history, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. This process, called recombination, allowed photons to travel freely for the first time. The radiation released at that moment has been stretching and cooling ever since, eventually arriving at Earth as microwave light. Mapping this radiation provides a snapshot of the universe at a very early stage, showing tiny temperature variations, only a few parts in 100,000, that correspond to the seeds of future galaxies and clusters. Thanks to missions like COBE, WMAP, and most recently the Planck satellite, scientists now have high-resolution maps of the CMB across the entire sky. These maps have revealed a remarkable degree of uniformity, confirming key predictions of the inflationary model. They have also provided detailed measurements of the geometry, composition, and early dynamics of the universe. But while the overall picture is smooth, some curious anomalies remain. A few regions of the sky show patterns that do not entirely fit with statistical expectations. Among these, the most famous is the so-called cold spot, an unusually large region in the southern hemisphere of the sky that appears to be cooler than the surrounding areas. Discovered in the WMAP data and confirmed by Planck, the cold spot spans several degrees of arc, much larger than typical fluctuations in the CMB. Its temperature difference is subtle, only a few microkelvin, but its size and profile have sparked significant debate. Some researchers have suggested that it might be a statistical fluke, a rare but not impossible fluctuation. Others have proposed more exotic explanations, including the possibility that it is the imprint of a collision between our bubble universe and another. According to eternal inflation, our observable universe resides within a single bubble that formed when inflation ended in a particular region of space-time. But inflation does not necessarily end everywhere at once. Other bubbles may have formed elsewhere, expanding and evolving on their own terms. In principle, these bubbles could collide if they are close enough, and such a collision would leave a mark, a localized distortion in the fabric of space-time, possibly visible as a circular pattern or temperature anomaly in the CMB. In 2007, a team led by Anthony Aguirre and Matthew Johnson developed a method for modeling what such a bubble collision might look like in the sky. They predicted that a collision would create a disk-like feature in the CMB with a specific angular size and temperature profile. Other researchers soon followed with their own models, expanding the theoretical framework and suggesting observational strategies. In response, scientists began scanning the CMB maps for evidence of such patterns. One major effort came from the collaboration of Hiranya Piris and her colleagues, who developed statistical algorithms to search for circular anomalies in the Planck data. Their analysis identified several candidate regions that might be consistent with bubble collisions, though none were strong enough to claim as definitive evidence. Another intriguing anomaly, often discussed alongside the cold spot, is the so-called axis of evil, a term originally coined half-jokingly by researchers noting that certain large-scale alignments in the CMB temperature fluctuations appeared to prefer a specific direction in the sky. This alignment violates the expected isotropy of the universe and has led some to speculate about large-scale inhomogeneities or even pre-inflationary physics. While many cosmologists believe these alignments are likely due to foreground contamination or statistical quirks, they remain a topic of active investigation. One of the challenges in interpreting these anomalies lies in the nature of the data itself. The CMB is a single realization of a random process. We only have one sky to observe. This limits our ability to perform traditional statistical analyses. Moreover, the signal is delicate and must be extracted from foreground noise, including emissions from our galaxy, interstellar dust, and other astrophysical sources. Even small errors in calibration or subtraction can produce apparent anomalies. Despite these difficulties, the effort to find signs of other universes in the CMB continues. It is one of the few avenues where a multiverse theory might produce testable predictions, albeit indirectly. A confirmed detection of a bubble collision would not only support eternal inflation, but would offer the first empirical evidence of a reality beyond our observable domain. There are, however, important caveats. Even if a circular anomaly is found, attributing it to a bubble collision requires ruling out all more mundane explanations, something that is difficult in practice. Cosmic variance, the inherent randomness of the initial conditions, makes it challenging to assign strong statistical significance to any single feature. Moreover, some models suggest that bubble collisions would produce gravitational waves, ripples in the fabric of spacetime, that might be detectable with sensitive instruments. The ongoing development of gravitational wave observatories, such as LISA and ground-based interferometers, could one day provide additional channels for testing these ideas. In the meantime, the search for CMB anomalies remains a powerful example of how theoretical speculation and observational science can interact. While the multiverse may lie beyond our direct reach, its possible traces ripple through the early universe in ways that might, just might, be visible. These searches also reflect a broader shift in cosmology, from modeling a single, static universe to considering a wider ensemble of cosmic possibilities. They invite us to view the sky not only as a record of our own origins, but as a potential window into other domains, other bubbles, other laws, other stories. And so the cold spot, the axis of evil, and other anomalies, whether they prove to be cosmic graffiti or statistical noise, serve as prompts to keep asking deeper questions. They remind us that the sky is not just a map of where we are, but also a reflection of how much we do not yet understand. As scientists examine the cosmic microwave background for subtle hints of ancient collisions between universes, the multiverse has been undergoing a very different kind of expansion into the world of popular culture. Over the past few decades, this once esoteric concept has made its way from advanced theoretical physics into comic books, blockbuster films, novels, television series, and even everyday conversations. But as the idea travels beyond the scientific community, it often shifts in form, shedding its mathematical origins and becoming something more imaginative, fantastical, and at times misleading. This cultural adoption of the multiverse is both a reflection of public fascination and a source of confusion. In science fiction, the multiverse tends to be portrayed as a realm of parallel lives and alternate histories. Characters step from one universe to another, encountering versions of themselves who made different choices, married different partners, chose different careers, fought different battles. Entire franchises have been built on this conceit, from comic book universes where superheroes collide across timelines, to films where dimensions overlap and reality itself can be bent or rewritten. In many of these portrayals, the multiverse serves as a narrative device, a tool for expanding storytelling possibilities without being bound by continuity or consequence. Writers can kill off a character in one universe and revive them in another. Worlds can be destroyed and reborn. Audiences are invited to explore what-if scenarios without the finality of traditional endings. This freedom has proven incredibly appealing, especially in long-running media franchises, where creativity sometimes runs up against the walls of established canon. However, the scientific concept of the multiverse, particularly in its modern forms, differs significantly from these popular depictions. In physics, other universes are not just different timelines where events unfolded another way. They are often separate regions of space, governed by different initial conditions, different symmetries, or even different laws of physics altogether. The idea that one could physically travel from one universe to another or communicate across bubbles is not supported by any current theory. These realms are not connected by portals or wormholes as they so often are in fiction. They are causally disconnected, sealed off by horizons, or separated by entirely different domains of space-time. Moreover, in science, the existence of other universes is not introduced to spice up a story. It is a consequence of trying to understand phenomena within this universe. Eternal inflation, quantum mechanics, and string theory each lead to multiverse-like outcomes, not because they aim for narrative intrigue, but because their equations suggest a reality more complex and layered than the one we initially assumed. Still, it is easy to see why the idea resonates so deeply. The multiverse offers a way to imagine lives unlived, choices undone, worlds unexplored. It provides fertile ground for both philosophical reflection and dramatic invention. And because it speaks to fundamental themes, identity, destiny, possibility, it has captured the popular imagination in a way few scientific ideas ever do. This popularity, however, comes with risks. When the term multiverse is used casually, it can conflate very different concepts. In popular media, the multiverse is often assumed to be synonymous with the many worlds interpretation of quantum mechanics, where every decision leads to a branching universe. But in cosmology, the multiverse might refer to different spatial domains created by inflation, or different vacuum states in the string theory landscape. These are distinct frameworks, each with its own assumptions, mathematics, and implications. Another source of confusion arises when fictional representations suggest that multiverse theories are accepted facts. While serious scientists take the multiverse seriously, they also recognize that it remains a hypothesis, an idea supported by indirect reasoning but not yet confirmed by direct evidence. When popular media presents the multiverse as a settled reality, it can give the false impression that physics has proven the existence of other universes. In truth, the field remains divided. Some physicists embrace the multiverse as a necessary implication of modern theory. Others caution that it may lie beyond the reach of empirical science. There is also the challenge of language. Words like universe, dimension, and reality carry different meanings in science and fiction. In scientific usage, dimension often refers to spatial directions or parameters in mathematical models, not to alternate worlds or timelines. Similarly, parallel universe in cosmology may refer to a separate inflationary bubble, not a world where Napoleon won at Waterloo or where dinosaurs never went extinct. Recognizing these distinctions is important not to diminish the role of imagination, but to clarify the boundary between speculation and science. The cultural multiverse is a rich and valuable space for storytelling, metaphor, and artistic exploration, but it should not be mistaken for a literal depiction of current physical theories. At the same time, science fiction has long served as a gateway to scientific thinking. Stories that stretch the imagination can inspire curiosity, spark interest in physics, and motivate the next generation of researchers. Many scientists have credited early exposure to imaginative fiction with fostering their fascination with space, time, and the cosmos. In this way, popular portrayals of the multiverse can play a valuable role, as long as they are approached with a sense of discernment. Some authors and creators have made efforts to reflect the scientific basis of the multiverse more faithfully, works that engage with the philosophical implications of quantum theory or explore the logic of eternal inflation, help bridge the gap between fiction and theory. Even in fantasy-tinged narratives, the echoes of real physics can prompt viewers to seek out deeper explanations, leading them from the screen to the textbook, or in some cases to the observatory or laboratory. One particularly interesting crossover has emerged in the form of philosophical and psychological explorations of multiverse themes. The idea that every possible version of oneself might exist in another universe raises questions about identity, free will, and meaning. If all outcomes happen somewhere, does choice matter? If other versions of us are living out different lives, how do we relate to the path we are on? These questions, while not strictly scientific, reflect the human dimension of the multiverse debate. They remind us that cosmology is not just about equations and measurements. It is also about our place in the cosmos, our capacity for wonder, and our hunger to understand the unknown. In the end, the multiverse's journey into popular culture reflects the same dynamic that drives science itself: the expansion of boundaries. Ideas that once seemed fringe or fantastical are now discussed at the highest levels of theoretical physics. And as these ideas filter into the wider world, they invite people to think more deeply about reality, possibility, and the vastness of what might be. As the multiverse permeates popular culture, drawing in audiences with its imaginative potential, the scientific community must reckon with a deeper, more fundamental question. Is the multiverse a scientific theory at all? Or does it fall into the realm of metaphysics, intriguing, perhaps even plausible, but ultimately untestable? This debate reaches beyond equations and observations into the philosophy of science itself. At the center of it lies a challenge that is as old as science. How do we distinguish between what is scientific and what is speculative? For many philosophers and physicists, the answer begins with the idea of falsifiability, a concept most famously associated with philosopher Karl Popper. In the mid-20th century, Popper argued that for a theory to be scientific, it must be testable in principle. That is, it must make predictions that could be proven wrong by observation or experiment. A theory that cannot be refuted, no matter what the evidence, is not a scientific theory. It is something else entirely, perhaps a philosophical system or a belief. Applied to the multiverse, this standard raises immediate concerns. If other universes are, by definition, causally disconnected from our own, separated by horizons, by quantum branches, or by incompatible physical constants, then how could we ever test their existence? No telescope can see across a bubble wall. No particle detector can capture data from a parallel branch of the wave function. From this perspective, the multiverse begins to look more like metaphysics than physics. It might be a logical consequence of certain theories, but without observational access, it remains beyond the scope of scientific validation. This criticism is not merely academic. Prominent physicists such as George Ellis have voiced strong objections to treating the multiverse as science. Ellis, a renowned cosmologist, has argued that the acceptance of multiverse ideas threatens to weaken the empirical foundation of physics. If we begin to accept unobservable entities as part of science, he warns, we may open the door to unfalsifiable claims of all kinds. Yet others see the situation differently. They argue that science has always worked at the edges of observation, using inference, prediction, and mathematical consistency to explore what lies beyond immediate reach. After all, many now accepted entities were once beyond observation. Black holes, quarks, and gravitational waves were all theoretical for decades before instruments confirmed their existence. In this view, the multiverse may be speculative, but it is not unscientific. Its various forms arise naturally from theories that are themselves testable. For example, eternal inflation predicts features of the cosmic microwave background that can be measured. The many-worlds interpretation is consistent with the formalism of quantum mechanics, which has been confirmed to extraordinary precision. String theory, for all its mathematical richness, is still being explored for indirect tests and constraints. Sean Carroll, a theoretical physicist and philosopher, has suggested a more flexible standard. Instead of demanding direct falsifiability, he argues for abductive reasoning, inference to the best explanation. In this framework, a theory is judged by how well it explains known facts, how coherently it fits with established knowledge, and how much new understanding it generates. If the multiverse helps us make sense of otherwise puzzling phenomena, such as the fine-tuning of physical constants, then it may deserve a place in scientific discourse. Another key consideration is theoretical fertility. A productive scientific theory is one that opens new pathways of investigation, poses new questions, and links disparate phenomena under a common framework. In this sense, multiverse theories have been remarkably fertile. They connect cosmology, quantum theory, particle physics, and even philosophy, suggesting deep relationships between seemingly unrelated domains. But how do we draw boundaries? If we relax the requirement of direct observation, how do we avoid sliding into pseudoscience? This is where philosophers of science play a critical role. They help articulate the criteria by which scientific theories can be evaluated, even in frontier areas where traditional methods may not apply. Some propose a layered approach to theory evaluation. First, does the theory reduce to known physics in the appropriate limits? Second, does it make novel predictions, even if those predictions are difficult to test? Third, does it offer explanatory power, clarifying puzzles or anomalies that lack alternative explanations? From this perspective, the multiverse is not a singular idea, but a collection of hypotheses with varying degrees of scientific strength. The inflationary multiverse may be more grounded because it arises from a framework that makes testable predictions. The quantum many-worlds interpretation may be harder to test, but it is internally consistent and avoids the conceptual problems of wave function collapse. The string landscape multiverse is perhaps the most speculative, though it emerges from a theory with a long mathematical pedigree. It is also worth noting that philosophical objections have not stopped scientific progress in the past. The Copernican model of the solar system was once criticized for its lack of empirical proof. The existence of atoms was debated for centuries before being confirmed through the kinetic theory of gases and later through electron microscopy. In each case, science moved forward by refining its methods and improving its tools, not by retreating from difficult questions. Still, there are valid concerns. If too many theories depend on inaccessible realms, science risks losing its grounding in observation. There is a danger of drifting into a form of intellectual cosmology that resembles theology more than physics, where beautiful ideas are celebrated for their elegance rather than their evidentiary support. One possible way forward is to treat the multiverse not as a conclusion, but as a hypothesis, a lens through which to interpret certain features of our universe. Like dark matter or dark energy, it may remain partially hidden but still guide research in meaningful directions. Scientists can continue to test the frameworks that predict multiverses, even if the multiverses themselves remain beyond direct reach. And in doing so, they engage in a long tradition of scientific reasoning, working at the edges of the known, balancing skepticism with imagination, and seeking to extend understanding while respecting the limits of evidence. As we continue exploring the implications of the multiverse, the philosophical dimension remains essential. It reminds us that science is not just a collection of facts, but a process, a method for building models of the world, refining those models, and knowing when to question them. The multiverse challenges our assumptions about simplicity, uniqueness, and what it means for something to be real. Building on the philosophical debate surrounding the scientific status of the multiverse, researchers have turned to another powerful tool to navigate uncertainty in a disciplined way: probability theory. In particular, many physicists and philosophers have begun using Bayesian reasoning as a formal framework to evaluate multiverse models, not just in terms of their elegance or internal consistency, but in terms of how well they explain what we observe, even when direct evidence remains out of reach. Bayesian reasoning is a method of probabilistic inference based on Bayes' theorem, which describes how to update the probability of a hypothesis in light of new evidence. It allows scientists to weigh competing theories, account for prior knowledge, and systematically refine their beliefs as more data becomes available. Though its roots go back to the 18th century work of Thomas Bayes, the approach has gained widespread popularity in recent decades across many fields, including cosmology, evolutionary biology, artificial intelligence, and even economics. In the context of the multiverse, Bayesian reasoning offers a way to grapple with a unique challenge: how to reason about things we cannot observe directly, but that may still have explanatory power, rather than demanding binary answers, true or false. Bayesian methods work with degrees of belief. A hypothesis is not simply accepted or rejected, it is assigned a probability based on how well it accounts for the known data compared to its alternatives. One influential advocate for applying Bayesian reasoning to cosmology is the philosopher and scientist Nick Bostrom. In the early 2000s, Bostrom proposed that when considering vast ensembles of possibilities, such as those implied by a multiverse, we must also consider the likelihood of finding ourselves in one type of universe rather than another. This led him to develop the concept of observer selection effects, where our own existence as conscious beings must be factored into how we evaluate the probabilities of different cosmological models. This is closely related to the anthropic principle discussed earlier, but Bayesian reasoning gives it a formal structure. Suppose we are comparing two theories, one that predicts a wide variety of universes with different constants, and another that predicts only a single universe with specific constants. If we observe that the constants in our universe allow for the existence of observers, then Bayesian analysis can ask, given what we see, which theory makes that observation more probable? If the multiverse theory predicts that many universes allow life, and the single universe theory predicts that life-friendly constants are rare or unlikely, then our observation of a life-permitting universe increases the posterior probability of the multiverse theory being correct, at least under the Bayesian framework. This kind of reasoning becomes even more powerful when applied to concrete questions, such as the value of the cosmological constant. As discussed earlier, this constant governs the expansion rate of the universe and appears to be incredibly small, yet non-zero. Its value seems fine-tuned to allow galaxies to form. If it were much larger, matter would have been spread too thin to clump together. If it were negative, the universe might have recollapsed too quickly for complex structures to emerge. In the 1990s, before the cosmological constant had been measured precisely, physicist Steven Weinberg used a combination of anthropic reasoning and Bayesian inference to predict that its value would be close to the maximum amount that still allows for galaxy formation. When measurements confirmed that the constant was indeed small but non-zero, just within the anthropically allowed range, many saw this as a striking success for the probabilistic approach to multiverse cosmology. Critics, however, remain cautious. They argue that Bayesian reasoning depends heavily on the prior probabilities we assign to different hypotheses, and those priors can be subjective or even arbitrary. For example, how should we assign a prior to the idea that the universe is part of a multiverse versus being alone? Should we weigh all possible values of the cosmological constant equally or favor some range over others? These choices can influence the conclusions significantly. To address this, researchers try to base their priors on the theory's internal logic, on simplicity principles, or on symmetry arguments. But there is no universally accepted method for assigning priors in cosmology, and this remains an active area of philosophical debate. Another complication arises from the measure problem, which affects any attempt to calculate probabilities across an infinite or vast multiverse. If eternal inflation produces an unbounded number of bubble universes, each with different physical laws, how do we define the fraction of them that are like ours? Without a well-defined measure, it is difficult to say how typical our universe is, or whether certain properties are probable or rare. Bayesian reasoning does not solve the measure problem, but it provides a structure within which to talk about it. It encourages scientists to make their assumptions explicit, to define what counts as evidence, and to clarify how different models relate to observations. In this way, it helps maintain scientific discipline, even when direct tests are unavailable. One of the strengths of Bayesian reasoning is that it is incremental. A theory does not have to be completely confirmed or refuted. Instead, its credibility shifts gradually as new evidence arrives. This is particularly useful in frontier fields like cosmology, where observations are limited and theoretical work often leads the way. Moreover, Bayesian analysis can guide future research by identifying which parameters most strongly affect the likelihood of a model being correct. It helps scientists prioritize which measurements to make next. For example, improving our understanding of the early universe's density fluctuations or refining the spectrum of the cosmic microwave background can narrow the range of plausible inflationary models, which in turn affects our estimates about the multiverse. There is also growing interest in using Bayesian model comparison. a statistical method that goes beyond assigning probabilities to parameters and instead evaluates which models as a whole better explain the data. This approach weighs the explanatory power of a theory against its complexity, helping to guard against overfitting or speculative inflation of assumptions. In this light, multiverse theories are being subjected to the same kind of scrutiny as any scientific model. They must earn their place through coherence, explanatory breadth, and alignment with known facts. Bayesian reasoning does not lower the bar for evidence. Rather, it provides a nuanced and transparent way to deal with uncertainty when traditional experiments are difficult or impossible. Some thinkers have extended this probabilistic approach into more speculative territory. Max Tegmark, for example, has proposed a classification scheme for multiverses based on their increasing degrees of abstraction, from regions beyond our cosmic horizon to branching quantum histories to variations in physical laws and ultimately to a realm where all mathematical structures exist as physical realities. In such frameworks, Bayesian reasoning becomes a necessary tool for navigating an ever-expanding conceptual space. Still, most physicists remain focused on the models closest to observational science. They use Bayesian tools not to justify belief in fantastical worlds, but to sharpen their understanding of this one, to weigh theories fairly, to extract meaning from noisy data, and to guide the construction of future models. In the end, probabilistic reasoning does not replace empirical testing, but it helps extend the reach of scientific inquiry. It allows us to reason carefully about the unknown, to quantify uncertainty, and to make progress even in the shadow of cosmic limits. While Bayesian reasoning provides a valuable framework for evaluating theories that stretch beyond direct observation, many physicists continue to ask a more grounded question. Can we test any of this in the laboratory? In particular, could the high-energy collisions produced in particle accelerators offer insights into the structure of the cosmos, or perhaps even into the existence of a multiverse? At first glance, particle physics and multiverse theory may seem like distant disciplines. One deals with subatomic particles measured in fractions of energy units, while the other concerns entire universes beyond our observable horizon. Yet the connection between the two is more intimate than it appears. Many of the theories that predict a multiverse, especially those rooted in string theory and inflationary cosmology, also make claims about what should happen at the smallest and highest energy scales. This opens a narrow but significant experimental window. One of the primary tools in this exploration is the particle accelerator. These machines, by accelerating particles to near the speed of light and smashing them together, recreate conditions similar to those just moments after the Big Bang. Among these, the most powerful to date is the Large Hadron Collider, LHC, operated by CERN near Geneva, Switzerland. With a circumference of nearly 17 miles, the LHC has enabled physicists to probe energy levels never before achieved on Earth. Perhaps the most famous achievement of the LHC was the discovery of the Higgs boson in the early 2010s. The Higgs boson is associated with the Higgs field, a quantum field that permeates all of space and gives particles their mass. This discovery confirmed the last missing piece of the standard model of particle physics, a remarkably successful theory that describes all known fundamental particles and their interactions, except gravity. However, while the standard model has proven extremely accurate in describing observed phenomena, it also leaves many questions unanswered. It does not include gravity, dark matter, or dark energy. It offers no explanation for the fine-tuning of fundamental constants. And it has nothing to say about why the universe exists in a state that allows complex structures, chemistry, or life. These gaps have driven physicists to search for physics beyond the standard model. One of the most widely studied candidates has been supersymmetry, or SUSY. Supersymmetry proposes that every known particle has a heavier superpartner, differing in spin. This elegant symmetry helps solve several theoretical problems, including the hierarchy problem, which asks why the Higgs boson's mass is much smaller than quantum corrections would suggest. Supersymmetry also offers a potential link to string theory. In many versions of string theory, supersymmetry is a necessary component, and the breaking of supersymmetry at lower energies could determine the vacuum state in which a universe settles. Different patterns of symmetry breaking could lead to different laws of physics, precisely the kind of variation suggested by the string theory landscape and the multiverse it implies. Thus, detecting supersymmetric particles at the LHC would not only confirm a major extension of the Standard Model, but also lend support to the broader framework in which multiverse scenarios arise. However, after years of operation and extensive data analysis, the LHC has not yet found clear evidence of supersymmetry. This absence does not disprove the idea. Many supersymmetric models remain viable, but it does constrain the parameter space. The energy scale at which supersymmetry might appear is pushed higher, making it more difficult to test and less likely to offer a natural solution to fine-tuning problems. This has led some physicists to consider a more radical possibility, that the parameters of our universe are fine-tuned not because of a deeper principle, but because of anthropic selection in a multiverse. If so, then the lack of supersymmetry at accessible energies might not be a failure of theory, but a clue that we are seeing one specific vacuum state out of many. From this view, our universe's properties are not uniquely determined, they are environmentally selected. Still, experimentalists are not giving up. The LHC continues to collect data at higher luminosities, and future upgrades will further increase its sensitivity. At the same time, proposals for next-generation colliders are gaining traction. These include the Future Circular Collider, FCC, and the International Linear Collider, ILC, both of which aim to explore new energy regimes and more precisely measure the properties of known particles. Beyond colliders, other experiments may also shed light on multiverse-related theories. Precision measurements of the Higgs boson could reveal subtle deviations from Standard Model predictions, pointing to new physics. Likewise, the search for axions, hypothetical particles that might explain dark matter, could intersect with string theory, where axion-like particles appear naturally. High-precision tests of gravity at submillimeter scales also provide constraints on extra dimensions, another feature of string theory. In some scenarios, gravity could leak into additional spatial dimensions, leading to deviations from Newtonian gravity at very short distances. So far, no such deviations have been observed, but the experimental bounds have improved significantly. Another intriguing possibility comes from the study of vacuum metastability. In quantum field theory, the vacuum is not simply empty space, but a state with a specific energy level. Some calculations suggest that our universe may reside in a false vacuum, a metastable state that could eventually decay into a lower energy configuration. If this is true, it could have profound implications for both particle physics and cosmology. Understanding vacuum stability requires precise knowledge of the masses of the Higgs boson and the top quark, both of which influence the shape of the potential energy landscape. Current measurements place the universe near a critical boundary between stability and metastability. This proximity is curious and has led to speculation about deeper principles, or perhaps the influence of a multiverse, in which only long-lived vacuum states are observed because others decay too quickly for observers to arise. Some researchers have even proposed that certain particle physics experiments, under extremely specific conditions, might create microscopic black holes or trigger vacuum decay. These ideas are speculative and remain purely theoretical at present, but they highlight the delicate connections between high-energy physics and the structure of the cosmos. Even if these efforts do not yield direct evidence for the multiverse, they still play a crucial role. By constraining theories, ruling out possibilities, and refining our understanding of fundamental laws, they help define the landscape in which the multiverse debate unfolds. Experimental physics provides the anchor that keeps speculation tethered to reality. In this sense, the search for new particles, forces, and symmetries is not just about filling in gaps. It is about testing the very frameworks that give rise to multiverse scenarios. If the theories predicting other universes also predict new phenomena in this one, then we can evaluate them in the laboratory, just as we do any scientific model. And so, while particle accelerators may not build portals to other worlds, they offer a more subtle and powerful tool, a way to glimpse, through indirect effects, the deeper structure of physical reality. They remind us that the smallest scales can hold the keys to the largest mysteries. As we journey from the machinery of particle accelerators toward ever more abstract ideas, we encounter one of the most ambitious and controversial proposals in the landscape of multiverse theories. While many models suggest the existence of other universes based on physical mechanisms like inflation or quantum branching, one proposal goes even further, arguing that all mathematically consistent structures exist as actual universes. This idea is known as the mathematical universe hypothesis, and it is most closely associated with physicist and cosmologist Max Tegmark. Tegmark's central claim is both bold and deceptively simple. The physical universe is not merely described by mathematics, it is mathematics. That is, every physical entity, process, or law we observe is fundamentally a mathematical structure. And if that is the case, then every mathematical structure that is internally consistent should also correspond to some form of physical reality. In other words, every possible universe that can be described by mathematics exists, not just in theory, but in fact. This hypothesis arises from a long philosophical tradition. The idea that mathematics is not just a tool for describing the world, but reflects something fundamental about reality can be traced back at least to the ancient Greeks. Plato believed in a realm of perfect forms, abstract, eternal truths that exist independently of the physical world. In modern times, many physicists have noted that the laws of nature appear to be deeply mathematical. From Newton's laws of motion to Einstein's field equations, from Maxwell's description of electromagnetism to the Schrödinger equation of quantum mechanics, nature seems to obey rules that are elegantly and precisely expressed through mathematics. Tegmark takes this observation one step further. If the universe is fundamentally mathematical in nature, and if mathematics is a realm of limitless structures, then why should our universe be the only one that exists? In this view, the question is not why there is something rather than nothing. It is why there is this something instead of all possible somethings. The answer, according to the mathematical universe hypothesis, is that there are all possible somethings. Every coherent mathematical system corresponds to a universe that exists in its own right. Tegmark organizes this vision into what he calls a hierarchy of multiverses, divided into 4 levels. Levels 1 through 3 correspond to ideas we have already explored. Level 1 includes regions beyond our observable universe with the same physical laws. Level 2 involves other bubble universes with different physical constants, as in eternal inflation or string theory. And Level 3 encompasses the many worlds of quantum mechanics. Level 4, the mathematical universe, transcends them all. It posits that every mathematically describable structure, regardless of its physical plausibility or resemblance to our own universe, is as real as what we experience. In this view, our universe is just one among an infinite collection of mathematical objects that exist in the same sense that numbers, shapes, and equations do. This raises several immediate and profound questions. If all mathematical structures exist, why do we find ourselves in one that allows life, consciousness, and complex structure? Here again, anthropic reasoning comes into play. Only a small subset of mathematical structures would permit the emergence of observers capable of asking such questions. Just as we should not be surprised to find ourselves in a universe that supports life, we should not be surprised to find ourselves in a mathematical structure capable of supporting computation, chemistry, biology, and thought. Supporters of the mathematical universe hypothesis argue that it provides a radical form of explanatory economy. Instead of needing to explain why certain laws of physics exist, or why constants have particular values, the hypothesis simply states that they exist because they are mathematically possible. Our universe is not selected or designed, it is just one of countless possibilities. However, the hypothesis also pushes the boundaries of what many consider science. Critics argue that it suffers from the same issues as other multiverse theories, but taken to an even greater extreme. If there are infinitely many mathematical structures, how do we assign probabilities? How do we define typicality or predictability? How can we hope to test the hypothesis when it includes every logically possible scenario? Moreover, some philosophers and mathematicians question the identification of mathematical existence with physical existence. Just because a structure is logically coherent, they argue, does not mean it has ontological status in the same way a physical object does. The distinction between abstract truth and physical reality remains central to many interpretations of mathematics and physics alike. Despite these challenges, the mathematical universe hypothesis has prompted valuable discussion, both within and beyond physics. It brings to the surface questions that often remain implicit in scientific practice. What does it mean for something to exist? Is mathematics discovered or invented? Why does mathematics describe the universe so well? Is that effectiveness a clue to the nature of reality, or simply a reflection of the way our minds are structured? Tegmark and others who support the hypothesis believe that future advances in physics may bring us closer to a purely mathematical formulation of reality, one that unifies quantum theory, gravity, and the structure of space and time. In such a view, the elegance of equations would not be a reflection of deeper truths. It would be the truth. Interestingly, this vision resonates with some interpretations of digital physics and computational universes. If the universe is a mathematical structure, it might also be seen as a kind of computation, unfolding step by step according to well-defined rules. This idea, sometimes referred to as the digital universe hypothesis, suggests that physical reality could be modeled as a cellular automaton or a vast mathematical algorithm. Whether one embraces these ideas or regards them with skepticism, they serve an important role in pushing the boundaries of inquiry. They force us to confront the assumptions that underlie not only our theories, but our entire conception of reality. In the process, they highlight the deep and sometimes uneasy relationship between mathematics and physics, between the abstract and the concrete, the ideal and the real. Ultimately, the mathematical universe hypothesis represents the furthest extrapolation of the multiverse idea. It suggests that not only might there be many universes with different physical laws, but that every possible universe exists simply because it can be described by mathematics. It replaces physical uniqueness with mathematical plenitude. As such, it raises perhaps the most humbling of all implications. In an infinite mathematical multiverse, our universe is not central, special, or even necessary. It is simply one logical structure among countless others. And yet, within it, we have evolved to contemplate the cosmos, to write equations, to build telescopes, and to wonder. Having followed the multiverse through the lens of inflationary cosmology, quantum mechanics, string theory, particle physics, probabilistic reasoning, and even mathematical ontology, we arrive now at the edge of the scientific map, a place where equations give way to reflection and certainty fades into possibility. Here, the question is no longer merely whether the multiverse is real, but what it means for science, and for us, that such a question can even be asked. Throughout history, scientific progress has repeatedly expanded the boundaries of the known world. From the realization that Earth orbits the Sun to the discovery that our galaxy is one among billions, science has shown a persistent tendency to humble our assumptions and widen our perspective. The multiverse, in many ways, is the latest and perhaps most radical expression of this tradition. Yet unlike earlier paradigm shifts, the multiverse does not simply relocate us within a larger space. It threatens to dissolve the idea of a unique universe altogether. It challenges the notion that the laws of nature are singular or necessary. It reframes our understanding of what it means to exist, and it forces us to confront a profound epistemological dilemma. How can we meaningfully investigate what we can never observe? Science has always walked a fine line between empirical investigation and theoretical extrapolation. On one side lies the hard ground of data, measurements, experiments, falsifiable predictions. On the other lies the open sky of theory, models, principles, and mathematical constructs that attempt to explain the data and reach beyond it. The most productive scientific revolutions come when these two sides reinforce one another. The multiverse, however, pushes that balance to its limit. For some scientists, this is a cause for caution. The fear is not that the multiverse is wrong, but that it is untestable. And if a hypothesis cannot, even in principle, be tested, then it may fall outside the domain of empirical science. This concern is not new. Similar debates have arisen over string theory, over the interpretation of quantum mechanics, and over philosophical ideas that masquerade as physical theories. But others argue that science must evolve to meet the questions it confronts. As observational tools improve, and as theoretical frameworks mature, concepts once thought untestable sometimes move into the realm of experiment. What matters most is not whether an idea is currently testable, but whether it is embedded in a broader framework that generates testable consequences. Eternal inflation, for instance, predicts features in the cosmic microwave background. Quantum theory makes precise predictions about the outcomes of measurements. String theory continues to inform models of particle physics and black hole thermodynamics. In this view, the multiverse should not be judged in isolation. It should be evaluated in the context of the theories that give rise to it. And those theories should be judged by their empirical reach, their internal consistency, and their ability to explain known facts. If the multiverse is a natural consequence of theories that succeed on other fronts, then dismissing it outright may be premature. But even if the multiverse remains speculative, it has already served a valuable function. It has sharpened our understanding of fine-tuning, of the role of observers, and of the assumptions we bring to cosmology. It has encouraged the development of new statistical tools, new experimental techniques, and new ways of thinking about space, time, and information. And it has connected fields that once seemed unrelated, linking cosmology to particle physics, quantum theory to information theory, mathematics to metaphysics. Beyond the technical details, the multiverse also touches something deeper, something fundamentally human. It speaks to our desire to understand not just the world as it is, but why it is this way rather than another. It invites us to imagine, to question, and to explore, even when the answers are not guaranteed. At the same time, it humbles us. In a multiverse, our universe is not central, not necessary, not even particularly special. It is one realization among many, a possibility made real by the unfolding of mathematics, quantum events, or cosmic inflation. And yet, within this small pocket of reality, we have evolved minds capable of grasping the idea of countless other worlds. That, in itself, is astonishing. For philosophers, the multiverse reopens ancient questions. What is reality? What is possibility? What is identity when other versions of us may exist elsewhere? For theologians, it raises new interpretations of creation, purpose, and uniqueness. For artists and writers, it provides an infinite canvas on which to project human imagination. And for scientists, it provides both a challenge and an inspiration, a call to push the boundaries of knowledge while honoring the rigor that makes science reliable. There is also a broader cultural context in which these questions play out. In a world grappling with uncertainty, complexity, and rapid change, the multiverse serves as both a metaphor and a mirror. It reflects our fractured realities, our competing narratives, our awareness of contingency. It invites us to see that other outcomes were possible, other paths might have been taken, and that the world we inhabit is not the only one we can imagine. In this way, the multiverse idea becomes not just a scientific theory, but a lens, a way of seeing the cosmos and our place within it. Whether or not it turns out to be physically real, it encourages a kind of intellectual humility and openness. It reminds us that the universe is vast, that reality may be more layered and subtle than we thought, and that our understanding, no matter how advanced, is always provisional. The question, is the multiverse real, may never have a simple answer. It may remain a boundary question, forever perched on the edge of physics, mathematics, and philosophy. But perhaps the more important question is, what do we do with the possibility? Do we ignore it because it challenges our assumptions? Do we embrace it uncritically because it satisfies our sense of wonder? Or do we explore it with care, skeptically, rigorously, imaginatively, knowing that even if we never reach the destination, the journey itself expands the horizon of human thought? In the end, science is not just a body of knowledge. It is a way of asking questions, questions that reveal not only the workings of the universe, but the nature of our own curiosity. The multiverse, whether fact or fiction, invites us to keep asking. It calls us to look beyond what is visible, to challenge what is familiar, and to stretch the imagination in pursuit of deeper understanding. And perhaps that is the most valuable thing it offers, not answers, but the enduring impulse to wonder.